You're all duly warned. My name's Ethan Smith. I am the field service rep for GA Larson. I am based out of Salt Lake City. We also have in the meeting with us Keith Wildhaber, who is our field service rep out of Denver. And I happen to be sitting in our commercial division, APS's office. And so we actually have two other guys in here that do Mitsubishi stuff. We have Sean back there. Wave, Sean.
Hello.
And we have Dan back there.
He left.
Oh, he left. He's leak checking a Mitsubishi system right now. So we've been building this stuff up all week and getting going on it. So if you hear banging and cussing, it's just Dan finding another leak in his system. So we're going to go ahead and get started though. So this is the advanced electrical class. This follows up our fundamentals of electricity class that we had about a month ago that Keith taught. The class is here for you guys. We're not doing it for our benefit. So if you have questions, please unmute yourself. Feel free to speak up anytime, ask questions. That's what the class is for, so you can get your questions answered. And so speak up anytime. I'm going to go ahead and put a slide up here that has all of the contact information for all the guys at GA Larson. We actually have 9 of us that do what I do. Oop, that's the wrong slide. Okay, and we want you guys to always be able to get a hold of us if you need to. So get rid of that window here. So we've got 6 of us listed here that do the residential equipment and light commercial. Like I said, I'm out of Salt Lake. Keith's out of Denver. We also have Steve Bukowski and Larry Lemons up in the Great Lakes region, and then we have David Filbert and Bill Snyder in the north central area of the country. And like I said, if you ever need help with Mitsubishi, a lot of us can help you with that as well. But tonight we're going to talk a lot about electricity. So, and we're going to start right off where Keith left off last time, which is with motors. And so last time when Keith's discussion, he talked a little bit about magnetism and electricity. And that's really what drives our industry forward is, oh, that slide doesn't want to work for me. It doesn't want to work for some reason. So we're going to go through it the hard way. So Keith started talking about magnetism, and magnetism is really what drives most of the operations in the HVAC industry. It's how our compressors work. It's how our switches operate. Our controls mostly are all operating off of magnetic devices. So we're going to start with motors. So one of the things Keith discussed in the last class was that the like charges repel each other and unlike charges attract each other. Same thing goes for magnetism. So here we've got a very rudimentary drawing of a motor here. And so we have a negatively charged coil of wire over here. We have a positively charged coil of wire over here. And then we have 2 permanent magnets. So we've got a positive end of a permanent magnet and a negative end of a permanent magnet. And so with them lined up with their like charges, they're going to want to repel each other. So they would repel each other and start to spin. And that starts the rotational force on our motors, getting that motor into a rotational operation. And then because it's alternating current that we're feeding this, so we've got 120 volts AC, the charge on the coils of wire is constantly flipping back and forth. So 60 times a second, we change the polarity on the coils in the motor. And so we're always switching back and forth so that we can repel and attract the like and opposite charges on that motor until we get that motor just spinning away and we get that thing to run and run and run and run up to speed. Okay. And so that's fundamentally how motors work. So there's lots of different kinds of motors. This is what would be referred to as a shaded pole motor. These motors simply have an alternating current of wire wrapped around an iron core. That iron core, when you pass electrical current around it, becomes magnetic. It projects a magnetic field down into the rotor, which has another magnetic field induced in it because of that primary magnetic field. And so we get like and opposite charges attracting and repelling each other, which causes that motor to start spinning. So that's the most basic motor we see. See these a lot on inducer motors, things like that. From there, we step up into something a little more complicated, where instead of having one coil of wire, we have multiple coils of wire. So now my slides should work at least. So there we go. And in this case, where we have our run winding, just like we did on our shaded pole motor, we also add a start winding. And so these start windings are actually arranged so that they're out of sync with each other. So you'll have a run winding here in the motor, and then you'll have a start winding that's kind of off to the side, kind of nests off to the side of it. And so that gives that rotor a little more starting torque. It shoves it a little harder, gets things running a little quicker. And then once it's up to speed, there's actually a little centrifugal switch on that motor that opens that winding up and takes it out of circuit. We actually do see these quite a bit in our industry. Anybody ever seen one of these or know where you might find one? I just realized I shut my audio off here. Anybody know where you might find one of those guys?
Would it be like a Taco pump, something like that? I see them on. They got a centrifugal switch.
Yeah, some of the old Taco pumps, some of the old Bell and Gossett pumps had a centrifugal switch in them. You see these almost universally in swamp coolers too. Once that swamp cooler motor's up to speed, it drops that that switch drops the start winding out and just runs on the run winding. So yeah, some of those old Bell and Gossett pumps, the old Taco pumps, that's exactly what that click was when the thing got up to speed, is that centrifugal switch dropping out. Okay, from there we can get even more complicated. We can start adding capacitors to these things. So we've got a start capacitor in series with that start winding. So while the start winding is physically out of phase with the run winding, the start capacitor will actually cause that to be physically and electrically out of phase with the start wind, with the run winding. So it gives it an even bigger kick. Of course, once that thing's up to speed, then we want to drop that thing out. You'll see these a lot on air compressors, where once it's up to speed, it drops out. You see this on things like bench grinders, stuff like that will have that centrifugal switch and a start capacitor. So you've got a lot of start torque on it. There's kind of a picture of what we're looking at there. So this is the stator of that PSC motor that we were just looking at. We've got the rotor here. That's a shaded, that's a cage style rotor. So what this is it's got actually different metals here. So you've got a set of bars that runs up at an angle through this rotor, and then you have a bunch of laminated steel plates that sandwich into the middle of those bars. And the way that's designed is, as these coils energize, they induce a magnetic field in this that helps drag that rotor around. But if you look at this, we've got actually two windings here. We've got our stator, which is the big one, like right here, and we're actually using 1, 2, 3, 4, 5, 6 run windings in this stator. And then you see this other fine, smaller coil of wire, and that is our start winding. So I think I've got a little better picture of that right there. So there's my run winding, big heavy gauge wire. And then we've got the start winding, which is a smaller, lighter gauge wire, and it's physically out of sync with those other ones. So it kind of bridges the gaps between those magnetic fields, helps lead that rotor around and get it spinning, gives it a little extra torque. But in the two motors we've discussed so far, that start winding drops out once that motor is up to speed. Okay. So one of the interesting things about this is if your motor is all shredded out, you don't have the labels on it, you can actually figure out what the RPM of your motor is. Okay. You can do that by counting the number of poles or windings. So we've got, in that motor we just looked at, we had 6 poles. We had 6 run windings on it. And you can actually take that and do some math. So we've got a universal constant, which is 7,200. So that's what you would get on a motor if you had only had 1 pole. So you take 7,200 and divide it by the number of poles. This particular one we're looking at has 8 poles. And that would equal a 900 RPM motor. Okay, so you take 7,200, which is the fastest motor you're going to get to run without any auxiliary controls on a single phase service at 60 hertz. And you divide that by 8, and that will give you your RPM output of that motor. Kind of a cool little thing here. So if we had 4 poles on that motor, thing would run at 1,800 CFM. RPM, excuse me. Okay. So there's some other examples there. We've got that 6-pole motor that we looked at. That's a 1,200 RPM motor. The 8-pole, 900. Okay, so let's talk a little bit about motors. So one of the other kinds of motors we have is what's called a permanent split capacitor motor. So here's a drawing of one of these guys. I'm actually going to flip over to another camera. We're going to do some exercises on this. And we're going to take a look at these motors and how they work. So let me switch my camera over here. Stop screen sharing. Okay, so we've got that same drawing right here. We've got an electrical meter, and we've actually got that motor that's in that drawing. Okay, so it's got a permanent split capacitor motor here. I think we've got the right capacitor on it. I've got a 5. Is that a 5 microfarad? Yes. Okay. This is just like a little blower motor that we would have in a furnace. But have any of you guys ever walked up to a blower motor in a furnace and there's no wiring diagram, there's no nameplate on the blower anymore, you don't know what the speeds are? And that ever happened to anybody? We got a quiet group tonight.
Yeah, sure.
You'll admit to that. What'd you do?
Well, you can, not that I remember how, but I think if you check the resistance of each winding, you can see what the speeds are.
Okay, so let's do that. We're going to go ahead and ohm out. So in this one, we know that my neutral is the white wire. So we're going to label that one white. Okay, and we're going to check resistance from the white wire to all these other wires. Okay, so the first thing we have to do is find a wire that gives us a resistance. So because I don't have any colors labeled here, we're just going to pick one, and I'm just going to write the resistance values down here. So which one are you on, Keith?
I can go to black.
So this is white to black. That gives us, according to the meter, which you guys are getting glared out on, 3.5. Sean, can I get you to turn the perimeter lights off? See if we can get the glare on the meter to go down here.
So they can actually see it.
There we go. So white to black was 3.5. Then we'll go, what's your next one?
Let's do blue.
So white to blue,
4.6.
4.6. And then you've got a red there.
6.7.
6.7, and a yellow.
5.3.
Okay, so if you're looking at this motor, we know the white is neutral. Which of these, so what color would D be? So I got terminal D right here. What color would D be? I'm going to zoom in here so it's a little easier to see. This guy. Back it up just a little bit. So we've got all the resistance values. Just look at this thing.
Would it be 3.5?
So yeah, that's my lowest resistance because that one's going to be closest to my neutral wire. So we're going to go, my resistance is 3.5 ohms. Okay. And so then we can just climb the ladder, can't we? So what's next? C is going to be what color?
Blue.
Yep, because that's 4.6. And then we go to
Yellow.
yellow at 5.3. And then the last one is
Red.
red. Okay, and that's because that's 6.7. Okay. And one thing we didn't do is get our capacitor because we've got a little bit of winding out here. Okay, so if we didn't know what that was, we can do that. So let's grab the meter real quick. Grab my lovely assistants back here. Okay, we know that's wired up to the capacitor, but just as a check so you guys know, we've got our capacitor out here. Bring that over here, if you would.
You gonna check capacity?
Yes. Well, we're not going to check capacitance, but we're going to check what the resistance is on this piece of winding here.
Oh. $74.
74 ohms. Okay.
Want to check the other one?
Yeah, check it to the other side.
It's isolated already.
And so you can actually tell which side of the capacitor is which when you do this. So that one's 7. So we can tell that this wire right here is this one. We have any identifiers on these, or are they just both brown? Yeah, they're just both brown. So sometimes on these cap wires, you'll have one with a stripe on it, but you can tell which is which because this one right here is 7 ohms. But this one right there is, what was it, 74?
71.
71 ohms. Why do you guys suppose that this little piece of winding here is such a high resistance?
Is it the start winding?
That is the start winding. So this is the start winding. And then all of this would be considered our run winding. All the way down to neutral. Okay, so that start winding is, remember, that thinner gauge wire, and it's a lot longer. Okay, so a combination of the length of the wire and the gauge of the wire makes that resistance higher. Okay, so that's how you can tell which one is your start wire, where your start winding is. So that also tells you where your neutral is too, because your neutral is going to be between the smallest and the largest ohm readings you get. That's your neutral terminal. Okay, make sense? Everybody on the same page? Any questions? Okay. So that tells us what our ohm readings. Now, do we know what speeds these are yet?
No, I don't.
Is there any way to tell from the ohm reading what speed everything is? Not necessarily RPM, but lowest to highest?
I would assume the lowest RPM would be the fastest, or the lowest resistance would be the fastest spinning, but I'm just guessing.
Okay, anybody else?
I would think the opposite, 'cause I think the low would be more like of a torque. Then it starts amping up to your high, and that's where your highest would be the 7.
I would vote for the first guy's response. Lower resistance, going to be more current, so it's going to spin faster.
Okay, so you're absolutely right there. The lowest resistance is going to be more current, so it's going to spin faster. So let's prove that though. So we've got a clamp on amp meter here and a little power supply. So we're going to wire this bad boy up. And I'm going to move out of the way here, and I'm just going to record numbers. Well, Keith gets us set up. So we can take some amp draws. We'll just hang that off the table.
Don't want to touch your leg.
Yeah, we're gonna try and do this without getting lit up. So I've got a neutral wire here. And we've got our ground so that we don't get lit up as easily. And we're going to start with that black wire because that was our lowest, right? So low resistance should equal high current. So we're going to put our clamp on amp meter here. And we'll pull this out a little bit. Okay, there we go. And I'm going to get another marker here. We'll record some amperages. So go ahead and start that up, Keith. Okay. So we got 6.7 amps on the meter. Okay. Pretty respectable for a 3rd horsepower motor. So the next one in sequence is going to be blue. Take that amperage reading again. And we're at 3.7. And then let's go yellow. That puts us at 2.3. I don't know if the audio is coming through to you guys, but the tone of the motor changes every time we do this.
Red, right?
Yep. So there's red. And 1.6. So physics still works.
You can slide off.
So there's our numbers there. We got 1.6, 2.3, 3.7, and 6.7. So yes, your lowest resistance reading is going to be your highest speed because that's going to create the most current for you. Now, something interesting that happens here is when you put your neutral in here and your run winding is just this, becomes just this little section of wire right here. All of this actually gets added to your start winding because now it's out of the main circuit and it's in the start winding circuit. Whereas if we have my neutral to red, we give up some speed, but we operate at a lower speed because, and that's assisted by the fact that we don't have as much start winding anymore. Because now I'm utilizing this whole winding as my run, and my start winding is just this little section down here. Any questions? Okay. So we've also got a spot for voltage here. So what I want to show you guys something is we'll lead into our capacitor section. So we're feeding this unit 115 volts. And we're currently wired up to the red wire. So if we're wired up to the red wire, what would you expect the voltage to be at any point along this line, guys? From neutral to any point.
you would assume 120, but I think it would drop as the further down the line you go.
Yep. Okay, so let's check. So we're gonna do, he's gonna stab his meter into the neutral here. And then we're gonna take a voltage reading on red while it runs.
That might be difficult.
Maybe. Don't try this at home, kids. We'll find out. Let me get this amp meter out of your way. Okay. No, we didn't get it in. Didn't go in. Maybe
Might be on our neutral side.
we're gonna. What's that? Oh, why don't you just shut it off for us? We're gonna try and move this probe around here.
I think it's this one. Hang on.
The joys of live demonstrations. And give that a shot. Nope.
Yeah, we just can't get in here.
Okay, so let's do this. We're going to pick up neutral up here. Why don't you pick up neutral up there? Now we're going to go about this, and that's ground. And then we're going to just go, so we don't have to do the balancing act. The math tells us that red's going to be 120 volts because that's what we're feeding our hot side off of. We'll see if we'll give it one more try here and then we'll move on. Go ahead. You're almost there. Yep, so there's 122 volts. So that's our line voltage. So when we're on red and white, we get 122. Now, while it's moving, if you'll just test these other ones, so go to yellow.
Wait, what's
So yellow's 108.
blue? 94. Black. 80.
Okay. So who said that it would drop as we got closer to neutral?
I guess I thought that, but
Okay. So anybody else who thought that, you're absolutely correct. Okay. Now let's move our hot from the red down to the black. And while Keith does that, what do you guys think is going to happen to the voltage at all of these points once we move that hot voltage down to black? We're going to put another voltage reading out here.
I almost think it's going to go up. I don't know though.
Anybody else?
It's gonna get lower as you get further away.
Going to get lower as it get further away?
Crap test.
Well, I'm gonna say that the voltage is gonna be a little under 122 because you're drawing more current. It's gonna bring that voltage down a little, but I don't really know what's gonna happen to the blue and red and yellow.
Okay, so we could be pulling more current here, so our voltage could drop there. Let's check. So you into, let's get into black if we can. Oop. Our piercing leads are not so piercing anymore. Give it a shot. So we're 121.5. So if we had a voltage drop, it's half a volt. So So let's go to blue. Still in the neutral. Yeah. So now we go to 140 here. And yellow. And red.
179.
Yeah.
Okay, so our voltage climbed as we went downstream. Why do you guys think that happened?
To me, it kind of just looked like it, for some reason, it'd be a step-up transformer, but I don't know why.
Okay, you're going down the right road. Let's test this one more place. We're going to test it at the capacitor. So I'll hold this here. And we're going to do that over here. Go ahead. So we've got 412 volts here. Go ahead and shut it down. Yeah, I am chicken. That's scary. Okay, so between neutral and here, we've got 412 volts. Okay. So someone mentioned a capacitor, a step-up transformer, excuse me. Okay. I'm going to point something out about this capacitor if I can get it to focus. Come on. And not glare. Come on. Right here. Focus there. Maybe, maybe not. Let's go down here and I'll try and zoom in. There we go. So this capacitor is rated at 370 volts. Technically, it's not the right capacitor for this unit. I've got some other capacitors here, though. We can check their voltage ratings. So this one's rated for 370 or 440. Got a little 3 microfarad capacitor here for 370. This one's up to 440 volts. Okay, so we can see why our capacitor voltage ratings are so high, because something's happening in these motors to boost our voltage somehow. What do you guys think's happening? Why don't you chew on that for a second?
The coil is acting, or the coils are acting like a generator.
Ah. Okay, so as we have this rotating magnetic mass, it's acting a little bit like a generator and inducing current into all these windings. So the more winding we have between, when we're running on black, we've got all this winding here between D and C, and that acts like a coil in a generator. So when we measure voltage between neutral and black, we get our line voltage because that's where it's being utilized. But when we go between neutral and blue, or neutral and yellow, and neutral and red, we have all this extra coil here that's generating power for us. So that's why we see the voltage steadily rise, 140, 160, 179. And then when we come over to our capacitor over here, we have that giant 71 ohm start winding plus all of this to generate power for us. And so we get 412 volts being threaded into the terminals of that capacitor. And so this is what we call back EMF. And EMF stands for electromotive force, or in layman's terms, voltage. Okay. And this is because we've got that big magnetic mass that's sending out magnetic fields through all of this extra winding that's not currently being directly powered, and it's generating alternating current that we see down here and up here and up here and up here. Okay. And so that's why when you look at capacitors, usually the capacitor rating is anywhere from 3 to 4 times what the standard voltage rating is for the motor. And so if you look at your motors, it'll actually tell you what your capacitor voltage rating should be. So we've got a 5 microfarad capacitor that's supposed to be rated at 370 volts. Okay, so it's important that you observe that when you're sizing capacitors, because we're going to have this back EMF, and this all runs back to having magnets interacting with coils of wire. Okay, any questions about this, guys? Okay. So I have a question for you then. So knowing what we know about this motor, we've got our start winding down here. We've done all the analysis that we need. I'm going to pull this out of the way and grab a clean sheet. And we know that that's black, blue, red, and yellow. Okay, and this is our neutral. What would happen if we used a different terminal for neutral? Okay. So let's go back to my, where'd my ohm chart go here? So, yeah, I'll just put rough numbers in here, 6.7, 4, 3, 2.3, approximately for our ohm rating. What if I were to take my neutral and say move it to the blue terminal here? What do you guys think would happen?
Nothing good.
Nothing good? Okay.
I
Would the
guess
motor?
it would depend on where you put, wouldn't it depend on where you put your run wire then as well? Because your start is always going to be, well, assuming your start is always down there. What happens if you put your run on that, the one that's below it? I guess I can't see, is it brown or is it?
So these are brown here.
Yep, those are brown, black. Oh, the black. So what, I think something would happen different if you put it on black versus if you put it on red or yellow.
Okay, so we're always going to have 2 wires connected. What I'm proposing is we take our neutral and say move it to the C terminal here, which is the blue wire,
Yeah.
and then we keep our power wire on black.
Okay.
It run backwards.
Okay, so we've got 1 volt for run backwards.
I don't think it would run.
Or start smoking.
I think that falls into the nothing good.
I would vote for the possibility of a locked rotor, but it may spin, but it's
Okay.
going to overheat.
Locked rotor amperages. Okay, so you think the who thinks that the amperage is going to go up versus down?
I think it's going to go up.
Okay. Anyone else? Brandon says it's going to go up. Anybody for down? All right, no votes for down. Okay, so it's universally agreed that the amperage is going to go up. So amperage is going to go up. Where's that plugged into? Grab this power strip right here and plug it into that so we don't do anything bad. No, just this guy right there. We're going to change power sources real quick just in case something bad happens and doesn't take my computer down. If class suddenly ends when we try this, everybody dial back in. No, let's plug it into that. That's on a separate circuit. I checked. I think. So we're gonna plug this into a separate circuit from the computer here. with a little bit of protection.
Make sure you get that wedding ring real close to it too.
Yeah, we're definitely not field technicians anymore. We're all jewelried up. Okay, so we're gonna take the neutral wire and we're gonna move it to blue. And let's get all the tools out here. So we're gonna put an amp clamp on this guy. Make sure it's not gonna time off on us. Capacitor. Where did the capacitor go? There's my 5 microfarad capacitor.
Are you ready?
No, I'm not ready.
I'm the kill switch.
Oh, it'll blow on its own.
I don't think it's a.
Is that not?
I don't think so.
Are you in series with anything else? Okay.
Few Mitsubishi.
Okay. So we're gonna get on this capacitor here. We're gonna move some stuff out of the way so everything comes over. Okay, so we've got voltage across the capacitor. I'll hold that. We've got amperage and a motor. Okay, go for it. We have 41 amps, 20 volts, and something popped.
I barely touched it.
Is that power strip warm? There,
Not yet.
there's the distinct smell of burning winding in the room,
But it did run.
but it did run. You can keep going.
Now it tripped on its own.
Okay, now we've tripped a circuit protector. Okay, why do you guys think it pulled 41 amps? Wow, that thing stinks. Get it out of here.
Put back in the warranty bin.
We'll put it back in the warranty bin where it came from. Okay, why do you guys think it pulled 41 amps?
Well, I guess we're just going from blue to black. We just have that, whatever that resistance is in there between the two windings.
Yeah, so let's come back here to my real chart. So between blue and black, we only have 3 ohms of resistance there.
So if you divide that by 120 divided by 3, you're going to get 40, right?
Yep, you are. Okay, so just Ohm's law, your amperage equals volts divided by resistance. So funny thing is 120 divided by 3 is 40 amps. So Ohm's law is still true. It did run, however. Okay. Now, I don't know if anybody noticed it, but how fast was that thing running?
Quite a bit faster.
It was moving, guys. Okay. Because we had a much shorter run winding and much more start winding, because what we effectively did is, if you guys pay attention to the numbers here, this coil of wire right here is much bigger than any of these segments. This coil of wire is more than, well, it is about double this coil of wire. Okay. So when we took and put our power across this coil of wire, A, it's much shorter. So we're going to have issues there. And B, that shorter, smaller coil of wire is going to make us run faster, but it's going to do it at the cost of amperage. Make sense? Any questions? So for anybody who chose nothing good and amperage going up, you are correct, sirs. Fortunately, fire didn't come out of that one this time. We did this with a 1-horse motor a couple years ago, and there was almost a fire extinguisher event. Okay. That being said, where are we at? We are 45 minutes in. I'm going to give you guys a short 5-minute break. So go out, get a drink, go to the bathroom. When we come back, hopefully my room will have de-smokified. Guys, go ahead and pop out of this and back into our presentation. Anybody have any questions? Okay. Let's talk a little bit about capacitors. So a capacitor, guys, in reality is just two pieces of metal that have been separated by what's called a dielectric, which is a fancy word for something that doesn't conduct electricity. Okay. And so I don't recommend doing this, especially on older capacitors, but if you cut open a capacitor, you'll get basically a giant coil of wrapped foil. So let me switch over here. Oop, if I can hit the right buttons. Maybe not. Okay, so we've got a capacitor here that we've gone ahead and cut open. So this is just a little 3 microfarad capacitor. But if you cut it open, this is essentially what you get in there. So this is a piece of plastic foil that's got metal impressed into it on either side. And then there's another piece of plastic sandwiched between the layers. Okay, and that's all a capacitor is. It's just giant plates of metal. The thickness doesn't so much matter as the length of that metal. And you can see it soldered on both sides here, one to the interior and one to the last roll on this one. And what that does is it gives us a lot of surface area in a very small package. Now, the reason I say don't cut these open in the field, guys, especially the older ones, the older ones have PCB in them, which I can't remember the chemical that stands for, but it is highly carcinogenic. If you are going to cut one open, don't, but make sure when you don't, it says non-PCB on it. No, Keith, that does not stand for Pepsi and bourbon. Thank you. 5 o'clock where Keith is. Okay. But that's what a capacitor is. Now, we talked about sizing the voltage properly. Let's talk about sizing your capacitance properly. So, vitally important that that happens. Because if those plates aren't large enough, the size of those plates is important, because the bigger the plate, the longer it takes to charge up that plate with electricity, and the longer it takes to discharge. Now remember, a capacitor is meant to take a electrical signal and delay it essentially to that start winding. So that start winding then becomes out of phase with the rest of the motor and either helps the motor start or helps the motor run consistently. Okay, and so you have to have your capacitor sized properly so that you get the right amount of out of phase delay. Okay, so there's another picture of a capacitor. That's a naughty capacitor to open up. That's a PCB one. I did not do that. So that's what the capacitor is doing, is it causing that phase shift. So we've got a physical phase shift in just how the windings are positioned. And then we have an electrical phase shift that we can shift that even more by making that electrical field delay on both its charge and discharge cycles. So the greater that phase shift, the higher starting torque. But if you go up too high, you phase shift it past 90 degrees, we can have a problem. So if you put too big of a capacitor on there and you phase shift that start winding more than 90 degrees out of phase with the rest of your motor in some applications, it'll actually start to fight your run winding and actually cause you more problems. Okay, so let's look at a chart here. So this is a comparison on the, I think the same size motors we were just using. I did this a number of years ago. And we did 3 different capacitors. So I'll let you guys guess which capacitor this thing's supposed to be with. So we did a 3, a 4, and a 5. And and we measured the wattage into the motor, and that was 102 watts in the 3 microfarad, 125 in the 4, and 149. We did that with a watt meter. Thank you, Nathan. It's PCB as polychlorinated biphenyls. If you can't pronounce it, don't eat it, right? Okay, so wattage into the motor steadily climbs as we increase our microfarad rating. Okay, this is the amount of work we get out of the motor. So this is calculated, and we calculate out to about the same. So 49 microfarads, 49.2, 48.6. That's all within a reasonable margin of error. So that's not terribly significant. We do notice a slight dip on the 5 microfarad, but not conclusive. Okay, so there's our loss. Apparently my 104 got moved over for some reason. So we actually lost 100.4 watts in the 5 microfarad and only 75 watts in the 4, and we lost 53 watts. Okay, where do you suppose that wattage is going? What's it turning into, guys?
Must be heat.
It's all heat. We don't produce light with motors unless something's gone horribly wrong. And so, yeah, you're absolutely right. That is all waste heat. So 53 watts of heat versus 100 watts of heat on either end of the spectrum, that's a big difference. Okay. And so that translates directly to motor efficiency. Okay, we can actually calculate the motor efficiency this way. We can also look at current. We see the current draw go up steadily as we increase our microfarads. And this is where we see our RPMs. So we've got our RPM for the 3 microfarads, 125, 4 microfarads, 130, or excuse me, 1130, and the 5 microfarad is 1115. Now, which capacitor do you guys think is spec'd for this motor?
I'm gonna go with 3.
Okay. Brandon says 3. Anyone else say 3? I didn't catch that. Joe, I think something's wrong with your mic. Why don't you type it in if you can?
Okay.
Drew says 3.
3 sounds good.
Okay. 3 looks pretty good, doesn't it? Okay. I would agree, because you're losing efficiency. Even in the 4, there's not a significant RPM gain. Okay, so this motor is actually spec'd for a 3 microfarad capacitor. Okay, but just going up 1 microfarad, we get almost a 50% increase in efficiency loss. You go up 2 microfarads up to a 5 microfarad, and you've got a 100% decrease in your motor efficiency, with no appreciable gain in RPM, running amperage, anything like that in the positive direction. Okay. So yeah, so the rule with capacitors, guys, is your capacitor is considered good if it is within plus or minus 5% of its rating. I'm trying to get my camera to work here. So there we go. There's my capacitor there. And so if I have a 5 microfarad capacitor, if you look right next to it, and doesn't want to zoom in for me. Come on, focus. There we go. That 5 microfarad capacitance rating says plus or minus 5%. Okay, it's not a voltage reading, it's a microfarad reading, so it's plus or minus 5%. So what's 5% of 5 microfarads, guys?
0.25.
0.25. So my maximum range on that capacitor is what? 4.75 to 5.25. That's my operating range. So I can't simply sub out a 4 or a 6. So here's another one. This is a little different brand of capacitor here. This is a 40 microfarad capacitor, plus or minus 6%. So how much range do I have on that one, guys?
2.4.
2.4. So I could be as high as 42.4 and as low as 47.6. Quick math. Okay. But everybody's capacitor is going to be a little different. That's a plus or minus 6. As they get bigger, sometimes that tolerance increases, but here's a 55.5 plus or minus 5. Again, plus or minus 5. And I don't know if this one shows it. Yes, this one does. So this is a multi-tap capacitor, and that's plus or minus 5%. So universally, the rule of thumb on capacitors is plus or minus 5%, you're good. Outside of that, we go back to the problem where we are talking about motor inefficiency loss, and we're just causing extra heat. So what does extra heat do to motor windings, guys?
Cause them to smoke.
Yep, you're going to have premature motor failure.
Higher amps.
Higher amperage, all the bad things. So we don't have to miswire the motor in order to get the nothing good happening. There it is, right there. Okay, we can simply not do our maintenance, not check the capacitors, and we'll end up in that nothing good category eventually. Okay, so this is one thing that gets overlooked a lot when we're dealing with electricity and motors is people just don't check the capacitors. Okay. So let's talk a little bit more about capacitors. So we dealt with this one, guys. This is a run capacitor. That's the motor we were just working with. So it's just using that capacitor there to put that start winding slightly out of phase just to increase the efficiency of the motor a little bit. Okay, so this capacitor is always in circuit. The other time we see capacitors in use is in an application like this, where this is a capacitor start and run. So we have a run capacitor, just like we had before, but then we have this extra capacitor down here, and this is a start capacitor. So you'll see this on motors that have high starting torque. You'll see this a lot on air compressors. You'll also see this on air conditioning compressors, especially in the age of non-bleed TXVs, where we anticipate starting under pressure and against a load. And so this is what's called a potential relay right here in the dotted box. And what this does is this relay has a little coil of wire right here. It's just like a normal relay, but that relay is wired in parallel with the start winding. And you can see that here where we pick up common on one side, we go through the coil of the relay, and we pick up start on the other side. Okay, so what happens in the start winding to the voltage when that motor is spinning? Anybody remember?
Goes up.
It goes up. That start winding voltage is the same as our capacitor voltage. Okay. And so that start winding, when that is running, is getting a lot of back EMF. So your potential relay has a coil that's sized for, if you look at the voltage rating on a start or a start relay, it's rated for the back EMF of your motor. Okay, so you'll have this relay will drop out at, in a typical compressor situation, somewhere between 370 and 350 volts usually. It will disengage, and these are normally closed relays. And so when it energizes that coil, it actually opens this up and breaks the circuit to that start capacitor, takes it out of circuit. So what this does is it gives us that extra phase shift with that start capacitor to give us a little extra starting torque on these high load motors. But once that starts, we don't want it to keep running that start capacitor, because that start capacitor is usually enormous and it's not rated for continuous use. It's only rated for use for, 1 or 2 seconds. And so when you see these things fail and they don't open up, or you get a compressor that doesn't start spinning and it keeps that start capacitor in circuit, the start capacitor actually overheats, and that's when you get the volcano of goo inside your condenser that came out of the top of that start capacitor. Because they're only meant to be in circuit for a couple seconds, but they give you that extra kick to get that motor spinning. Once it's spinning, generating back EMF, it opens up that relay and drops that start capacitor out. A lot of guys get really intimidated by potential relays because they don't know what's going on in them. But guys, it's just a relay in parallel with the start winding with a normally closed contact. That's all it is. Any questions about that, guys? Okay. So let's talk a little bit about supply voltage checks, guys. We didn't talk about this in Keith's class, I don't think. There's a couple voltage tests you need to do on everything you touch, especially if it's having troubles. You want a static voltage test. This is a voltage when the unit is at rest. You want an operating voltage test. And that operating voltage test needs to be within plus or minus 10% of your rated voltage. Okay. If you in a 120 volt circuit, that's going to be plus or minus 12 volts, which works out to your operating range for that unit is 108 to 132 volts. Outside of that range, we've got a problem that's got to be addressed, because it's going to destroy equipment at that point. 208, 230, your range is 187 to 253. When you're going out and doing maintenance on stuff, you should be checking your line voltage to your equipment. Voltage drop is what we see when equipment is operating and experiences a voltage drop when it starts operating. So this is a voltage drop from your static voltage. So if you take your static voltage and it's at 100 and 115, your voltage drop should be less than 2% when it starts running. If it starts running and you drop more than 2% on your operating voltage, that means you have an electrical problem upstream of your unit. Okay, you've got loose connections, you've got undersized wire. All those things are going to generate heat and premature failures. Okay, so on that 120 volt circuit, your voltage drop should be less than, let's see, 3 volts once that thing kicks on. Okay. Okay, so we talked about wires, loose connections, things like that. The other thing we need to address on electrical is grounding. So there's lots of improper grounding out there. There's the no ground situation, in which case anybody who touches it becomes ground. You've got a poor ground, meaning stuff's loose. It's not got enough grounding rod in the service. Or you can have stray voltages. This happens with frequency drives, high capacity motors. Rotating magnetic fields will generate stray voltages. A lot of the symptoms, especially in the furnace and air handler market, is you will get very erratic operation. Many of these units suffer from what we affectionately refer to as random error syndrome. If there's no ground, especially the furnaces. And troubleshooting, guys, is you've got to go back to your voltage checks. In a 120 volt system, that's really easy. You go to that ground, you check voltage between line and ground, and you should have your typical line voltage. That should match your voltage between line and neutral, and your voltage from neutral to ground in a 120 volt circuit should be less than 3 volts. If you have more than 3 volts, you've got a grounding problem. Okay. Most of the times you guys will go out there, it'll be next to nothing between neutral and ground, but your upper limit's going to be 3 volts in a residential situation. Okay. So we talked about that. The old rule used to be half a volt. On your low voltage, you can go R to C, you should have 24 volts. Common to ground should again be that same as your neutral to ground. And for some reason, I stopped there. Okay, so there's your voltage checks for grounds, guys. Both your high and your low voltage system inside a furnace needs to be grounded properly. Okay. Any questions about grounds or anything like that, guys, that we've covered? Okay, let's talk about three-phase for a second. So a lot of guys get intimidated by three-phase. We're going to demystify it for you a little bit. So three-phase power is how most electricity in the country is produced. We take what's called a three-phase generator, which is simply a giant three-phase motor, meaning it has 3 windings in it. We'll look a little closer at some three-phase motors here in a minute. And we rotate a magnetic mass inside those 3 coils of wire. So anytime we have a rotating magnetic field, moving that magnetic field through wiring, we're going to get induced voltage. We have a little demonstration of that. We've got ourselves a little generator here that we're going to go ahead and plug in. It's a very complex device here, guys. You get the other camera up. On the switch. Where'd my battery go? Okay, we have a three-phase motor right here. Okay, you can see in there we've got a set of magnets down here. I'm gonna switch my screen sharing off here. I have a little better screenshot here. Come on, focus. Come on, there we go. Okay, so we've got permanent magnets down in this motor, and we've got 3 coils of wire that alternate back and forth around this motor here. So as we spin this magnet inside this motor, we're going to induce voltage down these coils of wire. So we're going to go ahead and plug the meter in here. So I've got a drill on the other side of this motor. And we've got Keith there with the leads in. There's our meter. So as I spin this motor, you can see those magnets spinning around. We're starting to get some voltage. We're spinning it rather slow, so we don't get very much voltage. As I speed up, we start to see that voltage climb. In fact, if I take this drill all the way to the top, we've actually got 192 volts. So as we reduce the speed on that, that voltage drops proportionally to how fast we're moving those magnets around. Okay, and because it's three-phase, we can get that same voltage anywhere. Okay, take it all the way up to 92, and it goes all the way up. So we can actually make this thing do something useful for us. So I'm going to go ahead and plug this into my power supply. We got to plug it back into a good outlet. And we're not actually going to use the power supply to power this. I'll turn that off. Turn that off for me. much as I love working with live wires.
Should be wired.
Okay, so go ahead and we're going to plug a light bulb into this thing indirectly. So we've got a little light bulb down here. And I'm going to spin this. And once we reach the threshold of the light bulb, go ahead. Come in there a little bit. It'll turn this light bulb on for us. As we run it up and down, we can control the brightness of the light bulb to a certain degree. Pretty sure the light bulb's not rated for 192 volts though. So we won't do that very long. Okay, but we are legitimately creating power here. So the other thing we can do, because we're generating three-phase power off of this, is we can actually power a three-phase motor. So we have a second motor here that we're just gonna stub into this guy. And the point I'm trying to make by this, guys, is three-phase motors are the exact same thing as power generation. Okay, so I'm going to turn this one this way.
Yeah, let's keep this from short now.
Yep. We're going to move the whole contraption over here so that they can see the shaft on that one. And this one. Get on there. Okay, so all we've got is these motors, two motors connected, and we'll go ahead and spin one. What do you guys think will happen to the other one?
It'll start working.
Okay,
Will
you
be
think it'll
energized.
spin faster, slower, same speed? Brandon says it'll start.
Probably slower.
speed.
Windings aren't as big as normal electric.
Okay. Well, let's try here. So we'll see if we got this wired up right. So I'm just going to start out real slow here.
Opposite directions.
You notice we're going opposite directions, right? So here's the cool thing about three-phase. If we want them to operate the opposite direction of what it currently is operating, all we have to do is switch two wires. So if you ever go out to a rooftop unit and you got a fan moving backwards, hopefully your spade terminals aren't as tight as ours. No, maybe we hope they are actually. Okay, you can simply take two wires and reverse them. Okay, so we just took two wires there, we reversed it, and go ahead and start this guy. And you can see they're spinning it both the same direction now. Okay. And whoever said that it'll operate slower, you are correct, but only just.
There's some efficiency.
There's some efficiency losses between the two motors in the windings, but you'll notice that that right-hand shaft is moving slightly slower than the left-hand shaft. Okay, but we can take this, we can spin it up. And we can spin it down. Okay, we're just using a three-phase generator to power a three-phase motor. The faster we pulse those magnetic fields through the motors, from the generator to the motor, the faster that motor is going to spin. This is the same way that variable speed drives work, guys. Variable speed drives are just taking a motor, turning it into a three-phase motor in most cases, and changing the frequency and the voltage that run to that motor. So the higher the frequency, the higher the voltage, faster that motor will spin. Cool? Any questions about this, guys? Okay. Go ahead, just set that down on the ground. So these are just two variable speed motors out of furnaces. We've just taken the brains off of them and wired them together so that one's a generator and one's a motor. Any questions about how that works, guys? Thank you, Dan. So let's go back here. We'll go back to our generator. So we can see that we're getting alternating current off of all three of these things as we move that magnetic field back and forth. We're simply pulsing 3 legs of power to a single device. Okay. In fact, when we talk about single phase power, it's kind of a misnomer because we talk about single phase power as 120 and 208, 230. In reality, 208, 230 is 2-phase power. Okay, if we want to get technical about it. We call it single phase just for simplicity's sake because we don't have the 3 phases and we got to do stuff to start motors. But where we have a three-phase load, we're simply taking power directly from the grid and pumping it right into the loads. Okay. In fact, there's probably 3-phase power in your residential neighborhood. This is how they transmit power to the point of use typically. It usually gets converted in a neighborhood transformer station and then pumped into houses as two phases instead of 3. And they balance the load between all 3 phases in the residential market. Okay. But in the commercial world, 3-phase is king. Couple reasons for that is when we're going from a three-phase generated power to a 3-phase load system, we have less efficiency losses. It's easier. We don't have to do quite as much balancing, things like that. Okay. That's one of the reasons that we use 3-phase in commercial. Also, motors typically don't need any start systems, unlike in a single-phase system where we have to have a run capacitor and then a start capacitor. We can get away with just running those 3 legs of power that are equally out of phase with each other, and that gives us enough starting torque to start most things. Okay, so if you look at the sine waves on these 3-phase power, you'll see that everything is exactly out of sync with each other, 30% or 33%, whatever you want to call it. Then if you break down the motors, they all pretty much look like this. They may have more or less coils of wire, but your phases are just 1, 2, 3, 1, 2, 3, 1, 2, 3, all the way around that motor. Okay. The cool thing about that is on a typical single phase, a cycle from one point back to that point is 1/60th of a second at 60 hertz. But this, with 3-phase, that motor is getting hit with 120 volts every 180th of a second. Okay, that voltage is peaking on one of those windings every 180, is peaking 180 times a second. So we're able to give lots and lots of starting torque to motors with 3-phase systems. Kind of cool. Okay, so 3-phase power supplies. So 3-phase power supplies have the same problems as single-phase power supplies in terms of troubleshooting. You want to do your voltage checks. Also, we need to do ohm checks a lot more with 3-phase because our 3-phase systems, especially motors, need to be balanced. Okay, so when we're dealing with a motor, we should have equal resistance on all 3 legs, and we'll show you that in just a second. Okay, so let's move from 3-phase to its grown-up cousin, variable speed systems. So let's talk about variable speed motors. So there's a few different types of variable speed motors out there. There's ECM motors, which is short for electrically communicated motors, or electrically commutated motors, however you want to put it. There are the X13 or CTM motors, which we'll get into. And then there are also serial motors that we deal with in the HVAC equipment. These are all variable speed controlled motors to one degree or another. Okay, the way this works, guys, is we're feeding these things single phase power. So we're feeding them in 120 volts. They go through some electronics, which splits it into a DC voltage. That DC voltage is then spit out into a system of high-speed relays, 3 of them, which turn it into essentially 3-phase power. So you'll notice we've got our motor down here. We've got 3 legs of power on it. They all come up to these 2 gates, one from the negative side of this system, one from the positive side of this system. And this electronic control is going to fire these relays in sequence in order that we get essentially what is 3-phase power out to this motor. So we're pulsing each winding in time with the others so that we're exactly 33% out of phase with all of the other motors so that we get that rotation. The cool thing is with a frequency drive or a variable speed control like this is it can actually sense that the motor is spinning by the back EMF that it sees between cycles. And so what you'll sometimes see these motors do when they start up is they'll actually rock back and forth to find their location and then start. So sometimes you'll hear people talk about this motor growled at me and then started. That's what that's doing. It's finding its rotational location before it starts firing those relays. Okay, so this is what all variable speed systems operate in the HVAC market. Is there some version of this going on, and there's usually a 3-phase motor downstream. So when we talked about those motors that we just had, we were doing the generator demonstration on it, that's what these are. These are variable speed motors out of a furnace. Okay. So that's all started back with the ICM-1. I currently have a $50 bounty out there. If anybody ever runs into one of these things in the wild, I will give you $50 to mail it to me. They look like this. There's a giant aluminum block with a heat sink on them and then a motor. So if anyone ever sees one in the wild, get in touch with me. I'll pay you for it. Because I've only run into a couple of them in the field that still operated and didn't have the prescience to take a good picture of one. So these were the first foray in the residential market into variable speed blower motors. They worked, but they were extremely susceptible to moisture damage, and they tended to not live very long because they had this open controls box here. But they very rapidly moved on to the ECM 2.3s, which is what we see out in the field today. This is just one of those things broken down. And so that actually has a 3-magnet rotor on ball bearings, and then we've got our 3-phase motor windings around it, and then we have a frequency drive on the back of this guy. Okay, so we're using that electronic package on the back of the motor to drive the motor, manage that 3-phase system so that we can run this thing up, run it down, change the frequency and the voltage that we're delivering to those windings, and get that variable speed functioning. The biggest advantage to the homeowner on this is efficiency. Okay, they're higher efficiency than PSC motors, which you typically run about 40 to 60% efficiency. A variable speed motor is going to typically run 80% plus electrical efficiency. We also get the added benefit that we can control the airflow more precisely and that we can maintain that airflow through a wide range of static pressure changes, so restrictions to airflow. This is not to say that a variable speed blower motor is the cure for bad ductwork, much to the contrary. The only cure for bad ductwork, guys, is good ductwork. What a variable speed motor will do to your bad ductwork is make it louder. Okay, it will also shorten the life of the ECM. So just a side-by-side comparison of a PSC motor here and an ECM motor. Because we're dealing with 3-phase, we've got no start winding. We're simply alternating coils in here. So this one is about a 4. No, it's a set. No, it's not. I'm screwing up here. 1, 2, 3, 4, 5. This is, I think, a 6-pole 3-phase motor. So we've got 6 repetitions of the 3-phase. I'm too lazy to count, but I think it's 6. Okay. Again, we're going to have typically some type of permanent magnet on the rotor, as opposed to a PSC, which is using that cage rotor. And in the furnace motors, we're typically running ball bearings on both of these things, on both ends, simply because it's easier to lubricate a ball bearing at low speed versus a sleeve bearing. Okay, so how do you troubleshoot one of these? Well, this module that sits on the back of the blower motor is what we affectionately refer to as a black box. We can't really test it directly, but what we can do is test that we're giving it the right inputs and see if it's giving us the right outputs. So the first thing to test on a variable speed motor is the high voltage input. So this is the harness that you'll see inside a furnace typically. Inside an air handler, it's still going to be a 5-pin, but there's not going to be that jumper in there. That jumper tells this motor whether it's being fed by 120 volts or 230 volts. So in the air handlers, you'll have this jumper removed. In the furnace, that jumper will be there. But these motors are actually receiving 120 volts all the time in the furnaces and air handlers. So they should always have 120 volts to that motor. So that's the first thing to check. If we don't have high voltage, motor's not going to run. Okay. The other thing to do is we can give this thing what's called a go, no go test. So this is that typical 16-pin harness that we see on these ECM 2.3s. You'll notice that there is a blue and an orange wire on one end. That is to denote terminal designations. So that blue wire is always going to be pin number 1. That orange wire is always going to be pin number 9. Okay. But if we feed 24 volt common into pins 1 and 3 and 24 volts hot into pins 12 and 15, we can actually get this motor to start. We're sending in an artificial call for G. And so that motor is going to run at 50% of cooling speed at that point. Okay. We do make, there is a kit out there to make that easier. There's your part number right there. Okay. And you can order this kit and it comes as a prefabricated harness to do that go, no go test. Conversely, there are some tools out there, grab me that will do the same thing. So this is grab me that serial motor tester. This is my original TechMate that I bought a long time ago. And it has that 16-pin harness. It's got a few more wires in there because I can actually give it speed commands for cooling, fan on, heat mode, and various other fan speeds. And all I do is plug this in, make sure I've got 120 volts power, and then I feed it 24 volts power through these two jumpers off of my furnace board. So you can get tools like this. The modern TechMates are simply glorified go, no go harnesses. I don't recommend them as much. I'm more partial to the Zebra tester these days, which has more functionality like this one. It's a little more money, but in my opinion, well worth it. The Zebra testers will also work on everybody's motors. And you can get adapters to do even some of the other stuff that we're going to talk about a little later. So a good tester is key if you're going to be in the residential heating and air conditioning market, as almost everything is going higher and higher efficiency motors. And as we see the death of PSCs and furnaces, you're going to need something to help you diagnose these variable speed motors. So I bought this about 17 years ago. I've used it a lot. I've also made my own go, no go harnesses out of furnaces that I've pulled out. Strip that 16-pin harness. I don't care whose furnace it is. Pull it out, figure out what pins you are, and you can actually make one of these if you're intrepid enough. Not a big deal. I'll give you a chart later in this presentation you can take a picture of, and that'll tell you how to build it. Okay. So after we've done our go, no go test, that should cause, I'll get to that one. That should cause our motor to turn on and spin in cooling speed. If it does, we know that the motor is okay and the frequency drive is okay. At that point, we know we've got a control board problem. Conversely, if it doesn't turn on the motor, now we need to get into the brains of the backside of the motor and do a couple things. One of those is an ohm check. So once you take the end bell off that motor, you'll have a little module in there. There's a picture of an older one. Here's a picture. Here's one of the newer ones that you'll see out there. They all basically will all have a harness that goes between that module and the motor itself. You can see he's unplugging that one badly right there. We can't really test the module, but we can do some ohm checks on the motor to see if the windings are intact. So here's one with a plug on it. He's just got 1 meter lead in there, and he's going to check to ground between all of those leads. You should have an open line to ground on all leads of these variable speed motors. Okay. The other thing you need to do is you need to check resistance between all 3 legs of the motor. This is a 3-phase motor. They should be all pretty close to equal. In fact, we want those to be no more than 10% different from each other. So we have 3 of them here. We got 3.2, 3.1, 3.1. You can add those together. 9.4 divide by 3. That's our average ohms of resistance. As long as these 3 resistance levels fall within 10% of that average, our motor is okay. So these are obviously all within 10%. Because 10% would be 0.3, and we're all within 0.1 of that average. So this motor is okay. If you have an open line or you've got an imbalanced motor, you probably need to have that motor replaced. Usually when you have that happen to a motor, it's gonna take the drive with it. So you're gonna need to replace that end bell at the same time. So you replace both components of the motor in that case. There isn't a fixed resistance for motor windings. So we've got 2 different motors that we tested here. This is a 3.1 resistance winding. This is a larger motor, and that's going to have 10.5 ohms of resistance on those motors. So it's not so important what that reading is, but that it's within 10% of everything else. Any questions, guys? Okay. So there's some pictures of the old ECM2s and 2.3s. One of the things you'll notice about these guys is the typical mode of failure for those power heads is this little resistor right here. This is a current limiting resistor. This makes sure that the motor doesn't run away with itself. The reason that this resistor fails typically is due to high static in the ductwork, because that motor will try and speed up so that it gets what airflow that's being requested of it. But this is like the rev limiter in your motor. Okay, it's going to hit this current limiting resistor. It's going to say, oh, it's a negative temperature coefficient resistor. So when the voltage goes up and that resistor gets hot, it's going to drop the voltage downstream and cause that thing to slow down and cause this to cool down. You do that enough, and eventually that resistor is going to fail. It may look like that. It may look like that. Okay. These resistors are non-replaceable items. I know that you can go out on Alibaba and buy them. I do not recommend that you install them. These are a safety device. If you take this out and defeat it, or take the 2 stubs of bare wire and twist them together, you're defeating a safety device. So if this resistor has failed, A, you need a new power head, and B, you need to find out why it failed. Go start taking some static pressure tests, look at the ductwork. You know, it could simply be that the guy only changes his filter every year, you know, or every 6 months. Maybe have a conversation about getting them on a maintenance agreement so that happens more often. Otherwise, you're just going to be back, or somebody else is going to be back, and your homeowner is going to badmouth you to the next guy. Yeah, this thing failed 3 years ago. I had it replaced. Dead again. You know how the story goes. But that low current limiting resistor dies because of high static situations. Okay. So this is a sneaky little chart. And what this is this is the pinout and what it does to in all of these pins. So we mentioned that pin 1 is common. So we've got pin 1 down here for common, and pin 3 is common. Okay, so this is how you build your tool. You can build your tool with switches that have jumpers. between R and any combination of these pins. And you can make this motor do whatever you want it to do because we have inputs for our auxiliary heat airflow. We have inputs for our fan on and off. We've got inputs for Y1. We've got inputs for W1, W2. We can even put our own indicator light in there to tell us what is going on, how many CFM we're getting, okay? And so all this little Gentech tool I have is a glorified jumper box that jumps pins together. Okay. So if you want to build your own tool, that's the manual that you need. So there's the publication number there, right there, and that will get you started. That has this chart in here, and you can figure out how to build your own tool, or you know, if you're a nerd like me, or you can just go ahead and buy a Zebra tool and they'll do it for you. Okay, but there's that chart. If someone wants to take a picture of it real quick, there it is. There's a video that goes through everything I just mentioned. This video is posted on a website that's run by Train and American Standard called fieldtechhelp.com. Great little resource out there for you guys in the field. It has way more than just ECM motor videos on there. I encourage you guys all to look at it at some point. We'll look at one of the other videos that's on that in just a minute. Okay. So the good news is that ECM 2.3 was a great little motor. It has been phased out by Gentech, and so they've phased that out in favor of their new Eon platform. The Eon motor modules are backwards compatible to the ECM 2.3 motors. Has the same connectors, uses the same mounting bracket, but they've reduced the controls package size. So this is sized to go into their motor. Their motor has space to accommodate those two bumps. Obviously, ours is not. So they do come with an adapter ring when you get these and a spare set of bolts. Okay. You're probably going to reuse the bolts that came off of your existing motor because they will be long enough. These bolts here are for the newer style motors because they're shorter. But what you're going to do is you're going to put that adapter ring on it. There is a tab and a notch on the motor that you need to line up, and a notch on the motor plug that you need to line up. So make sure you're getting everything aligned, put that adapter ring in, screw your two bolts together, and you will have a Eon motor conversion. That'll look like that. Any questions about that, guys? Okay, let's talk about CTMs really quick. So a CTM is a DC driven motor. So it's got all the efficiency gains of a variable speed motor, but it has 1/10 of the brains. Okay, so these are up to 9 programmed levels of torque. These do not adjust for CFM based on static pressure, but you get the efficiency of that motor. You don't have quite the CFM range, and they suffer with high static, but you get a lot more efficient motor. This is why we had the FAR rule a couple years ago, where it took all of the PSC motors out of blowers in furnaces. And we went to these constant torque motors from those PSC motors. Okay. These can be programmed by every OEM manufacturer out there. And they set them to a torque value, which is basically a speed that this thing needs to operate at. So it's going to run at that constant torque value no matter what. Okay. We do get a little better performance on high static than we do out of a PSC, but that gain is pretty marginal. Okay. So these can be programmed for up to 9 speeds. And when you look at the plugs, this is what you'll see. So across the top of the plug, you'll have a line, a neutral, and a ground, and a 24-volt common terminal Across the bottom, you'll have speed taps 1 through 5. Okay. So these are your low voltage connections here. And these are your high voltage connections. You'll notice that the high voltage connections actually have smaller spade terminals on these ones that have plugs so that you don't get them confused. Okay. All of the X13 motors will physically have 5 taps, but they can be programmed for up to 9 speeds. We'll talk about how that's achieved. We already talked about the benefits a little bit. Okay. Let's check for proper operation. So again, this motor is a frequency driven motor. And so it has 120 volts powered to it all the time. So you're going to check for a high voltage source and you're going to check for a low voltage signal on these motors. If you have both of those things and the motor runs, the motor is good. If it doesn't run and it has both of those things, the motor is bad. That's it. That's all the diagnostic you have with these things. Check for high voltage and low voltage. If you've got both of those, motor doesn't run, motor is dead. Look for water. That's what kills most of these things. Okay. So you can do that with your meter. Simply get on your 120 volt side and the low voltage side. So when these things launched, they only operated off of 24 volts and you only had 5 speeds. Okay. Back when they were sold under the Evergreen, now they're the Azure motors, all the same thing. We'd get a speed command off of the control board in 24 volts and it would say energize heat, heat, cool, cool, or whatever. And we get a speed command. Well, programmers are sneaky little bastards. And what they figured out is they could actually take this motor and instead of sending it 24 volts all the time, you could send it a DC voltage. And so we can send this thing a DC voltage to tap 1, 2, and 3, 4, and 5 and get 5 speeds. And then we can take it and actually send it DC voltage on multiple taps and get more speeds. So tap 1 through 5 is speeds 1 through 5. Tap 6 is actually a signal on tap 1 and tap 2 at the same time. Moving on to tap 7, same thing, tap 1 and tap 3, tap 8, tap 4, and tap 4 and tap 1 again. And tap 9 is simply tap 1 and tap 5 combined. And we can get more speeds out of this constant torque motor. Now this is a DC voltage chart out of a Train American Standard unit. We've got the 5 wires for low voltage that go out to the motor off of that control board. So that's just an example. There are other manufacturers doing this the same way. Okay, so this is just a picture. They may not always have those giant white plugs. You may just have 2 separate plugs, a high voltage and a low voltage plug, but the tests are the same, guys. Check for high voltage, check for low voltage. If you got both of them, motor doesn't run, dead motor. Okay. If you're not getting low voltage, but you're getting high voltage, when you should be getting low voltage, then we need to look at the wiring or the control board. But they're pretty simple, guys. Either it works or it doesn't when you give it the right inputs. Okay. There is a video online about doing that. We're not going to watch that one either, but I encourage you guys all to go out to that fieldtechhelp.com and take a look at the videos for yourselves. The last motor I want to talk about, guys, is the same as a variable speed motor. It's the newer version of variable speed motor that we're using in the Train American Standard equipment, and it's an upgraded system. So there's the ECM motor that we all know and love. The serial port motor gets away from this 16-pin plug. We still have the same power plug, that same 5-pin power plug, but we go to a 4-pin communications plug. And I've got a better picture of this right here. The other thing we do is we go from a 3-magnet motor to a 5-magnet motor. So we go from 6 poles to 10 poles when we go to this. So having those 2 extra magnets gives us a finer resolution on how we can control this motor. So we get better variable speed, we get finer control and better feedback from that motor to tell us what it's doing, having that five magnet rotor. Okay, so there's a picture of one. Some of them will have a plug connector like that. Some of them have plugs built into the side of the motor like this. Okay. But it's the same thing. We're sending a low voltage signal and we're always feeding it high voltage. So your first diagnostic check on this is, guys, to check to make sure you've got high voltage from the unit. Okay, that can be 208, 230 in the air handlers or 115 in the furnaces. After that, it gets a little more complicated because we're using a communicating signal on our low voltage pin. So we can't just check for voltage. We can do some voltage checks that'll tell us something, but the quickest way to test one of these motors is to do another go, no go test, where we're simply going to take the harness out of the board. Okay, so the board, you'll have a plug that looks like that. It's a four pin or 5-pin harness, depending on what your equipment is. And we're going to apply power to TX and ground. So you can see on these motors, we've got TX and ground here. And over here, we've got TX and ground. So this plug here is actually this guy right here. Okay, we apply 24 volts to that, and the motor should start at about 75% airflow. Okay, they make another go, no go harness just to make that easier, bypass having to shove wires into your thermostat or into your wiring harness. And that's this guy right here that you can see in my hands and on the screen. And this is just a go, no go test harness for that serial port motor. This plugs right into your motor, wires right onto your R and B in your furnace, and we'll do that go, no go test for you. Okay. So that's available out there. There's your part number. Okay. Various pieces of equipment are going to have that harness coded a little differently on the control board end, but that's all out there. So I'm going to actually play this video for you. A good buddy of mine, Eric Weiss, is the one that does all these videos. He's got one of those soothing baritone voices. And so he's going to tell us a little bit about some of the voltage checks that we can do on these serial port motors that will tell us a little more about how to figure out if it's the board or the motor that has failed. So I'm going to try and see if this will play. If you guys don't get audio, please let me know.
The air handler airflow control board or furnace IFC.
It's good.
What speed and what CFM we need to deliver. When we get into the diagnostics of the motor must always have 120 volts on a furnace or 240 volts on an air handler. The next step in diagnostics is to apply 24.
Turn it up a little.
So the very back two pins of the motor is going to be common and red for 24 volts hot. And when the motor has power and receives that 24 volt input, it's going to run at about 75% capacity. The motor does communicate with the control board. So you can see right now the furnace isn't idle, but as soon as I disconnect my communication from the motor and the board, I'm going to get an E17 for an alert. And that tells me I have a blower communication error, in which case I'm going to be looking at my connections. Here it's obvious I disconnected it. It may be a loose connector within the pin, or it may be a broken wire between the motor and the control board. Once I reconnect, it'll recognize the motor communication and go back to the normal idle mode. And this is true of the 7-segment on the air handler and also the IFC on the furnace. Now the connector that I showed in the example can be ordered. That is publication 34-3454-01. And this harness can be ordered through ComfortSite and DealerNet under the Marketing Center and order marketing materials. Now the S furnace, the motor is behind the plate and the control board. So the easiest diagnostics on that is to ensure that I send 24 volt to transmit and ground, which duplicates what the wiring harness does. But here I can simply apply to the harness. So ground will go on the ground terminal for common, and I'll put 24 volts on the transmit,
Yeah, well,
and my motor is going to run at 75% airflow.
he's on the last video.
If my motor runs with a go no-go test, I need to continue with the troubleshooting process. If the motor does not energize when it has high voltage applied and 24 volts applied, and I follow the power cycle sequence for at least 60 seconds off, then I know that my motor has failed and I need to order a new motor module. If the motor did run, I'm going to start checking voltages from my control board. The black wire is going to be my ground on this test furnace, so I always want to reference my ground for all test points. And then the bottom connector here is going to be my 12
The
volt
charge
source.
assist doesn't work.
So from my meter, I see I have approximately 12.4 volts DC.
We need to charge it.
Now this DC reading is going to vary whether it's a furnace or an air handler because we run a different power supply within the control board. So look for a source voltage someplace between 12 and 14 volts DC, all depending on the unit. And if I see that, I know that I have source voltage that's going to be able to push the communications to my motor. If I do not have the 12 volt source voltage, I know that my control board is at fault and I need to replace the control board. The next element I'm going to check is my transmit ground. Now this is the individual packets that the motor is sending. So transmit on my control board is going to move to receive on my motor. And I can see my TX here is pulsating about once a second. And it's going to run between 0.7 to 1 volt DC from what I can read on the meter. If I'm looking at an air handler control board, I'm going to see the pulse speed much more rapid. And I will see several packets being transferred every second. So the frequency of the pulse is not important. The fact that we are seeing pulses and voltages confirms that the control board is sending data to the motor. If I have 12 volt source, but I do not see any voltage on my transmit, then I'm going to condemn the board. If I do see pulses on my transmit, I'm going to go to my RX, which is the other white wire just below my ground. And here I can see my RX is very similar to my source voltage, and it is tied to the same power supply. So if I see that my RX does not change in voltage, I know that my motor is not sending any information back to my control board. But here I can see my voltage drop. And that drop of voltage is going to be at about the same pace that I see my transmit. And it confirms that my motor is sending data back to my control board. But for field diagnostics, I'm going to confirm the motor has high voltages. I'm going to apply 24 volts to the motor, and the motor should start up and run. If the motor does run, I will continue the diagnostics to make sure I have 12 volt source DC voltage on the control board. If I do not have 12 volt source, I'm going to replace the control board. If I do have a 12 volt source, I'm going to focus on the TX for transmit to make sure the board's sending voltage packets to the motor. If I see the pulsation, I'm going to move to the RX circuit, and I'm going to look for a slight drop in voltage from what I have from the source. Now, if I'm seeing a transmit pulse, but I'm seeing no receive pulse, then I know that I either have a broken wiring harness or my motor has failed. I'm going to remove the wiring harness at both ends, home out each one of the individual wires. Make sure my pin connectors on each one of the wires is going to be tightly seated within the Molex plug. And if my wiring harness is good, then I know that my issue is with the motor itself, and I will be replacing the motor. For further information on variable speed motor diagnostics, please visit our e-learning course. And in the course catalog, just type in variable speed motors and get an in-depth course on the variance between ECM motors, whether it's constant torque or variable speed, and also why motors fail. Thank you.
So that's just kind of an example of what's out there, guys. The Field Tech Help website is great. It is a free website. It's open to the public. You don't have to have a login to get to most stuff that's on there. It is maintained by Trained and American Standard, but it's got a lot of stuff on there that's universal between all brands. So if you're new to the industry, or you just need a refresher course, or you run across something new in the field, go to fieldtechhelp.com, see if there's something on it that would help you. All the videos, that's one of the longer videos that you'll see on there. They're made to be used by guys in the field who are up against a wall. If you can't get a hold of me during the middle of summer and I'm taking 100 phone calls and my response time's up in the hours to voicemail, go out to fieldtechhelp.com, see if there's something on there that would help you. There a lot of times you'll find something just like this, the ECM motor testing. There's several different manufacturers that are using this serial port motor. They all operate the same, okay? So That's all I have for class tonight, guys. If you guys have any questions, I'm more than happy to stay and answer them. But I appreciate you all coming and sticking around. That's class. Like I said, if you got questions, I'll hang out as long as you guys want to hang out and answer questions. But otherwise, thank you for attending.